Welcome to the Flip Learning Mode from KLU. I am Dayanti Mahapatra presenting the topic Reducibility and Computational Equivalence. So before going to that topic, first to know what is the aim of the section, what are the instructional objectives, and what is the outcome for the students. So aim of the section is define the reducibility and computational equivalence and identify different type of reductions and construction relation between the automata. The objective of the section is designed to define, explain and concept of reducibility and its applications, its computational complexity. Here there is computational complexity is written. It means we are define the P class, NP class and NP complete and NPR problems in the computational complexity. How much complex the problem is. So next is the understand the Turing reducibility and its implication for problem solving. So here we are reducing the Turing, using the Turing machine we will make the reducibility and also use the SAT problem and reduce it by through the Turing reducibility. So third point is analyze the satisfiability and relationship to the computational complexity. And the next will describe the Cook's theorem and the significance in the NP completeness. Here in this line we will prove the Cook's theorem. At the end of section, the student should be able to define and describe the reducibility and its role of classifying in the computer problem. Student will know what are the classification of the computational problems and also what is the Turing reducibility and understand its implications for the problem solving. Next, student should be know analyze the what is SAT problem and what is its relationship between the complexity classes. Next, students should also know the Cook's theorem and its importance in the establishing NP completeness. Apply the concept of reducibility and Cook's theorem to identify the NP complete problems and analyze their implications. Next, basically first going to that Cook's theorem or the satisfy problem, first to know what is the computational complexity, the P class problem, NP class problem and NP hard and also NP complete problems. P, NP hard, NP complete problems. What are the P class, NP class? P class means that problems are solved in the polynomial time. It means the class P is the set of decision problems that can be solved by the deterministic Turing machine in polynomial time. So we can take the example of the sorting problems. For example, sorting problems, suppose there are n number of elements and this we search element, we go up to n, and this type of element, this type of searching is the polynomial time, and also we can verify the element found or not in the polynomial time. So the P class problems are the problems which we can solve in polynomial time and also verify also in polynomial time. Here there is an example is given. Let's consider a Turing machine that recognize the even length polynomial over the alphabet 01. The machine should accept strings like the 001100. This is a even length polynomial and the Turing machine accept that, and also accept the 110011. Palindrome means the reverse is same, but reject the string like 101. This is the odd length, and also this is not a palindrome 001 0001. So this is not a palindrome. So that type of problem is solved by the deterministic Turing machine in polynomial time, also verify in the polynomial time, and that type of problem is the tactical problems or P class problems. Then we go for NP problems. It is a decision class problems or NP problems is if a proper solution is given, we can verify it, easily verify it. But it can checked by a deterministic polynomial time algorithm. Otherwise, if someone claims to have a solution of NP problems, we can efficiently verify the correctness of their solution in polynomial time. So a NP problem is given, someone will give a solution. We can verify the solution is correct or wrong in the polynomial time. So that class problems are known as NP problems. For example, suppose someone will say Sudoku problem, someone will be solve the Sudoku, we can verify whether it is a correct or not. And another example is a subset problem. Here that is given the subset problem. One class example of subset problems. So a subset sum problems. So given a set of positive integer is given, and the target integer positive integer is also given. So you take the subset from that set and make a sum to the target integer. If it matches, then you can take that subset. So someone will be solve that, and you can verify the solution is correct or not in the polynomial time. Here it is a example given. Suppose we have set of positive integers 3, 1, 4, 2, 2, and a target is given to 6. The subset problem asks whether there is a subset of these numbers whose sum is equal to 6. One possible solution is the subset 3, 1, 2. We can verify easily that 3 plus 1 plus 2 is 6. Then we go for NP-hard. A problem, suppose this is for example, suppose there is a MP class problems, we can polynomial time reducible that problem to all the NP problem to another problem. So that problems are known as NP-hard problems. It means a problem is NP-hard if the hardest problem, if in NP more formally language L, suppose language present in NP is NP-hard if every language L dash in NP there is a polynomial time 1 to 1 reduction to L. It means L is reduction to L dash. All the L elements of L is reduction to L dash, and that problem is known as NP-hard problem. So here the example of shared problems are the NP-hard problems with the conjunction and decision of the Boolean values. And also we are using NOT operators. This is given here. Shared problem is the NP-hard problem. You can given a Boolean formula which is a logical expression built from variables and or NOT operators. And the equation whether there exists an assignment of truth values, true or false, up to the variable makes the entire formula true. So we assign that variable 0 or 1 or truth or false. Finally, we got the truth value. That assignment is known as shared problems. So someone will be solved that. We easily verify that this is true. So next is the 3 shared problem. Okay, so here in the 3 shared problem, only 3 literals are given. Suppose you can take the literal A, B, C, like that, any X, Y, Z, we can only 3 literal are given, but this is the 3 shared problem, and also we can get the truth value. That also hardest problem of the NP. Then NP complete. Suppose we can reduce all the NP problems L to L dash. Then in the L dash, that some problems are the also NP. So that problems are also known as NP complete problem. It means the problem is in NP-hard and also in NP is known as NP complete problem. A problem is NP complete if it is in NP and every problem in NP can be polynomial time reducible. This means this is the you had a polynomial time algorithm to solve NP complete problem. You could use to solve all problems in NP also in polynomial time. So in the Venn diagram, it is written that so all program in NP it is reducible to the NP-hard. If some problem are also in NP, it is known as NP complete problem. Next. So next is the reducibility and Turing reducibility, circuit satisfiability, and also Cook's theorem. Reducibility means suppose a problem A is given and A is reducible to B. It means if we get a solution for B and also we also get a solution for, there is an algorithm, deterministic algorithm, we can make a solution for B. Also we can find the solution of A for that using that algorithm. That type of known as reducibility. And in the case of Turing reducibility is a specific type of reducibility based on the Turing machine, which are the abstract computational model. If we say that problem A is Turing reducible to problem B, It means if we can use one algorithm to solve B to problem solve A. If we can found a algorithm to solve the problem B, then we can also solve the problem A by using that algorithm. If otherwise, we can say if B is difficult, then we say A is also difficult. If B is difficult, then we say A is at least difficult as. SAT problem, again I can explain the SAT problem because it is used in the Cook's theorem. The Boolean satisfiability problem, SAT, is a classic problem in computer science and logic. It involves the determining whether given set of Boolean variables that satisfies a given Boolean formula. The formula type as the conjunction normal form CNF. It is in CNF form. CNF form means it is the disjunction and conjunction of literals. Suppose we say A disjunction of B. This is one literal and this is another literal, and the value is true. And that formula conjunction of disjunction of literals, and this form is known as CNF form, which is conjunction is and disjunction is or. This is the or and this is the conjunction is the and. So simple illustrate the SAT problem with a truth table. Suppose we have the Boolean formula of given the 5 literals. One, this is the B, C, D. There are 5 literals. So we can give 2 to the power 5, 32 values. Suppose there are 2 literal A and B, we can give 4 values 1, 0, 0, 0, 1, 0, 0, 1, 1, 1. So similar, if it is 5 literals, then we can give 32 values. And we can only here, we can choose the truth value. Satisfiability means we can only take the truth value. Here only the sum of the truth value is given. So A, B, C, D are the 5 literals. So there is 2 to the 5, 32 combinations. And we can take truth and false value. But we have satisfiable means only we can take the truth value. So we also verify, this is a NP problem. We also verify that in the, this in the polynomial time whether it is true or false. But this problem is also NP problem. And finally, we conclude of the SAT problem. What is the SAT problem? Circuit satisfiability referred to as a SAT is a well-known computational problem in computer science. It involves determining whether there exists an assignment of truth values. So we can check whether the assignment is given, whether it is true value or not. Here we can check whether it is truth value. We cannot take the false value. Only the assignment we can take the truth value. And in such assignment exists, the formula said to be satisfiable, otherwise it is unsatisfiable. Here Cook's theorem. Cook's theorem states that the Boolean satisfiability problem SAT is NP complete. So if you Cook's theorem said SAT is NP complete, it means if SAT is in NP and also in NPR, we say it is NP complete. For proof that NP complete, suppose we say B is in NP, all B is in NP, and B is polynomial time reducible to SAT. So we say it is in SAT is NP complete. So we prove B is in NP. Construct a function f that maps member of A to member of B. It means we will reduce member of A to member of B. So it means if X is in A and X is in B, so that f can be computed in the polynomial time. So here we use a function to reduce A to B, and f is the function, and also f is computed in the polynomial time. Here we will prove the Cook's theorem by SAT is NP complete and B is in NP. We say that B is also in NP, and we reduce polynomial times B to SAT. So that we can say SAT is NP complete. Here we say B is in NP, which is a non-deterministic tuning machine to solve that problem. Here by using a tabular we prove that B has polynomial time NDTM runs in. So here suppose k times for the Turing machine and the n rows, so it is all the rows it is n to the k, and for the all the columns we say the time complexity is order of n to the power k. And the steps are, steps 1, we will put the single value in the each cell. So each cell contains the single value, each cell contains the single value, and the first or the our starting configuration is the first row, and the next row derives from the previous row, and last row contains the accepting configuration. So we make a conjunction for row 1, row 2, row 3. Finally we can get the result or accepting step. Next, so here we can write suppose this is x, this is the position of suppose 0 0, and the symbol is hash, and finally we make the start row as like that, x00 hash, then next is the x01 q0. You check here, this is the x01 q0 and x02 w up to x n to the power k, up to x n to the power k minus 1 and hash. Final configuration is the combination of or the conjunction of x. Here is the x n to the power k minus 1 hash. This is the starting row or the start configuration of that Turing machine. Next, this is the accepting state of the Turing machine. Q accept all the ij belongs to between the 0 to n to the k, and the state xij is accept. This is defined as from the q0 we can got the from this state, first state we got or the second, third, like that. Here is the suppose acceptance state, and is the xij the acceptance state, and also it is up to between the 0 to n to the power, sorry, it is between 0 to n to the power k minus 1, n to the power k minus 1. That is then q accept is the, here q accept is the xij or 0 to the 0 less than ij between the 0 to n to the k xij, and q accept is the states, and in between that we derive the moves, how to go to first to second, the moves. Suppose this is A, this is B, this is q0, this is C, and these are the literals, and the next state is suppose in this q0 we can read this and go to left. For that we make C to D and or B to, suppose these are symbols, suppose A, B, C, D, A, B, C are given, and this is the suppose q0 is given here, and you read this and go to make it x and go to left. So previous all are same, what are present in the previous are set, and these two lines will see change, also changed. These are the same what are present, and this B will be x and go to q0, and these are the D. So these three rows, three columns and two rows are the changed. Makes B to x and go to right. So these three lines are changed. So here we can take 2 into 2 rows 3 columns. This one window contains two rows, either go to left or go to right. So this window contains two rows, and thus it is affect to the second row and also three column, either this column or this column. So here one window contain 2 into 3 columns, second like that, third like that, up to this is also polynomial time, which is the order of n to the power k. So this also n to the k, this also order of n to the power k. Also this is the order of n to the power 2k. Also this is also polynomial time. So we can reduce that problem also in polynomial time to SAT problems. So for that, SAT is NP complete. Thank you.